let's begin. The next homework assignment that you've got due, homework 10, is going to be submitted in an odd time. Ordinarily, your assignments need to be turned in before class on either a Tuesday or Thursday. But this next one you should submit before noon on Monday of next week. And then the following day, on Tuesday, the 16th, is when we're going to have our second midterm exam. So for that exam, I'll provide the same formula sheet that I've given you earlier. You don't need to prepare any kind of a note sheet. And it'll be covering chapters 4, 5, and 6. Now today we're going to be continuing some calculations related to fluid momentum. And in fact, we've got 3 examples that are all pretty quantitative and lots of number crunching. We're going to spend the vast majority of today's class just going over those specific examples because they are kind of types that repeat themselves not only just on the assignment, but more broadly they represent the basic principles of fluid momentum. So today we'll talk about jets and vanes, and then on Thursday we'll consider the more complicated case of momentum through pipes. Any questions on the announcements? Okay, so today we'll do fluid jets and vanes. And in the case of fluid jets, ordinarily the problem type is that some stream of fluid is being intercepted, meaning it's stopping, or we want to find out the amount of momentum flow from the jet itself. In the case of vanes, it's usually just redirecting an inflowing stream in some other direction. In today's lab, in 319, we're going to do some vane experiments where we have a jet of water coming up from, it's pressurized by the hydraulic bench, and then it's intercepting a couple of plastic pieces that redirect the flow, either just changing the direction of the flow by 30 degrees or 90 degrees or 120 or 180. And so what we're going to do is identify how those different angles change the amount of force that's imparted by the fluid jet. On Thursday, we'll move into nozzles and flow through pipes. But when we apply the momentum equation, this left-hand side of the equation has a really specific interpretation: the force required to hold the system steady. And so what we calculate from this equation is how much force would need to be applied to this vane, for example, so that it doesn't move in response to the fluid jet that it's intercepting. So it's really easy to accidentally get the opposite reaction from what you actually need to be calculating. So, for example, you can tell by looking at it, maybe previous experience, putting your hand out the window. That's kind of similar to a fluid jet and a vane. When you have your curved hand out the window, you know that your hand is pushed backwards because the fluid jet is impacting it. And so here, for example, the fluid jet would be moving this vane to the right if it wasn't supported by this part. And so the force required to hold this vane steady would be to the left. And also you'd have to press down. So it has both a vertical and a horizontal reaction. And so to refresh your memory, on the right-hand side of this equation, we're keeping track of the mass flow rate out. Remember that mass flow rate is a scalar. It doesn't have direction, and so we won't use any kind of a negative sign in the mass flow rate. But velocity is a vector which has both magnitude and direction. And so any velocity that would be to the left, a fluid jet that's acting to the left, would be negative in the x direction. If it's moving to the right in the x direction, then that's positive. So we have the outflow term minus the inflow term. So that's what we're going to apply in the 3 examples that we work through today. So here's the first of those. What we have is a water jet that's coming in, and we know the velocity of the jet of the water, 15 meters per second. So that is the velocity in the direction that's indicated. But what we need to do is break that velocity into its horizontal component and its vertical component. We know the angle that this jet is intercepting the tank of water. We know that the mass of the tank itself is 5 kilograms, and it currently has 20 liters of water. So we're going to be considering both the vertical and the horizontal reaction to this system that we're looking at. In the horizontal direction, there's a stop block that keeps this tank from sliding to the left, which is what it would do if this was like a frictionless surface and that stop block wasn't in place. Then the tank of water would be pushed over to the left. And then in the second point, we're going to consider the vertical forces. And so the force that's acting on the bottom of the tank, the table is pushing up on the tank in the amount that supports the mass of the tank itself, the water that's in the tank, and then also the force that's generated by that fluid jet as it intercepts the water. So we're going to consider this in the X and the Y direction. All right, so as a couple of starters, first of all, we have to figure out the cross-sectional area of the jet. We know the diameter of the jet, but we need to know the cross-sectional area because we're going to need that for the mass flow rate. Remember that mass flow rate, m dot, is the density of the fluid, the cross-sectional area, and the velocity. Now, I've seen on more than one occasion when people are substituting into the momentum equation, sometimes they will write, instead of mass flow rate times velocity, they'll write density, area, and velocity squared. Because this mass flow rate, you can see, is density, area, and velocity. So the reason why I point this out is that if you square the velocity term, then you'll be blinded to the direction that the velocity has. So if it's like a negative velocity because the stream is to the left, by squaring that value, you'd lose the negative sign when it comes to the force. So don't just square that, the velocity. What you have to do instead is calculate the mass flow by itself and then multiply it by the velocity. And so the mass flow rate will only be positive, and the velocity is sometimes positive and negative. So here in this example, I'll just write in order a couple of things you have to calculate. Okay, so first of all, calculate the area of the jet. Calculate the weight of the tank. Calculate the weight of the water. And then once we've got all of that preliminary data out of the way, then we're going to find the momentum in the x direction. So in the x direction, we want to know how that could, okay, in the x direction, there's no flow out. There's only flow in. So if I write the momentum equation here, the sum of the forces in x, meaning the forces required to hold the system steady, is the sum of the mass flow rate out, velocity out in x, minus the sum of the mass flow rate in, velocity in x. So you can see in the horizontal direction there's no flow out. There's only flow in. So what we're going to have is that the force required to hold the system steady is just the mass flow rate in, velocity in, times the cosine of 70 degrees. Because the cosine of 70 degrees is what will give us the velocity component that's in the x direction. All right, so let me pause here for a second, give you some time to begin calculating these initial parameters and then substituting it into the momentum equation in the x direction. All right, so just getting the preliminary stuff out of the way, the area of the jet is determined on the diameter. So I've given you the diameter in millimeters. We divide that by 1,000 to get 0.03 meters squared times pi divided by 4. So here's our cross-sectional area of the jet. And I've calculated the weight of the tank and the weight of the water. Both of those things won't actually be used until we're considering the vertical direction. For the horizontal, they don't yet matter. So here's the general momentum equation in the x direction. And since there's only flow in the x direction, no flow out, then the flow out term drops out. And we're just talking about the mass flow rate in and the velocity in the x direction. Now you'll notice that there's no little I, there's not an x after the I here. It's not the mass flow rate in the x direction, it's just the overall mass flow rate. And so what that means is that the angle doesn't come into play when you're calculating the mass flow rate. The angle only affects the velocity term. So here where I'm calculating the mass flow rate, you'll notice it's the density times the volumetric flow rate. Or in other words, density times area times velocity. And nothing about the angle goes into that calculation of the mass flow rate because we want to know just the overall mass flow rate. And we account for the angle only in the velocity term. Okay, so it's the fluid density is 1,000 kilograms per cubic meter, the area that was previously calculated, and then the velocity is 15 meters per second. And for the mass flow rate, remember, it doesn't have direction. So we don't put in the negative 15 meters per second because there's not anything like a negative mass flow rate. It's just 10.6 kilograms per second is entering the control volume. All right, so that's the mass flow rate that then is going to go into the momentum equation. And so it's the minus here is because in the overall momentum equation, we subtract the inflow term. So that's 0 minus mass flow rate in velocity times the angle that the component of the velocity that's in the x direction. So a cosine of 70, you can see from the figure, if we just kind of look at it, that most of that stream is vertical. Only a relatively small fraction of it is in the horizontal direction because 70 degrees is pretty close to 90 degrees. So it would make sense that only 34.2% of that stream is in the x direction. So that's what the cosine of 70 tells us. And so when we have the minus because it's an inflow, and then also the minus because of it being to the left in the horizontal direction, so minus 15 meters per second, then that's why the force required to hold the system steady is positive 54.4 newtons. Any questions about that so far? The force in the x direction? All right, now let's think about in the y direction now what we have to keep track of. The force that's due to the fluid jet in the y direction, the sum of the forces in the y direction required to hold the system steady will be the sum of the mass flow rate out, velocity out in y, minus the mass flow rate in times the velocity in y. Okay. So there's no flow out. There's just flow in the vertical direction. So the force due to fluid momentum in the y direction is going to be the minus of the mass flow rate in times the velocity times the sine of 70 degrees. So the sine of 70 degrees will give us the vertical component of that jet. And of course V is going to be negative because it's downward. Okay, so we previously already calculated the mass flow rate. So negative 10.6 kilograms per second. And that minus sign is structural to the equation. It's not in the mass flow rate itself. Kilograms per second. Minus 15 meters per second because in the vertical that jet is going downward. And then the sine of 70 degrees is 0.9397. So in the y direction, you would have to press upward to hold the system steady against the effect of the fluid jet. So this positive number here, 149.3, that's because we have to press up on the tank because the fluid jet that's coming down from above is pressing that tank downward. So the reaction of the table is to press up. But the overall force that's acting on the bottom of the tank is going to be that reaction to the fluid momentum, 149.3, plus also the weight of the tank and the weight of the water. So the cumulative net force is going to include all three of those components: the weight of the tank, the weight of the water, and the effect of the fluid momentum. So 394.6 newtons. All right, so from this example, we got a little taste of accounting for the direction of the velocity. Remember, an important lesson is that mass flow rate is a scalar, and so you shouldn't square the velocity term, even though algebraically it looks like maybe you could, since it's density, area, and velocity in this first term, and then in the second term is another velocity. We need to keep it separate because it's only in this second velocity term that we account for the angle and also the direction. All right. Any questions on that first one? All right, now let's consider this next example. This is a fluid jet that is spraying into a plate, and the plate has a hole in it. So this first fluid jet has a diameter of 10 centimeters, and then there's a hole in the plate. Some of the water is spraying outward radially. So we have to think in three dimensions here. If this is just a cross-sectional view, some of this spray is up, some of it is to the left and to the right. It's going in all directions radially, and we just want to know in the x direction what force is required to hold the system steady, and then the equal and opposite of that force is the external force that the jet applies to the plate. So now, this question is asking you to calculate the force in x, but then it's actually asking for the opposite of that force. The last question was saying what force is required to hold the system steady. This one is saying what force does the jet apply to the system. All right, so we know the two diameters, we know the velocity, and what we're assuming, look, the inflow velocity is the same v as the outflow velocity. So this dashed line represents our control surface, and we can look at the stream that's going in, the stream that's going out. They're going to have different mass flow rates. So m dot out and in are different, even though the velocity in and out is the same. So you'll have to calculate mass flow rate in and mass flow rate out. And we're assuming that this is water. So the density will be that same 1,000 kilograms per cubic meter. All right, on this problem, the mass flow rate in is big, and the mass flow rate out is small, because we've got a larger diameter for the inflow stream and a smaller diameter for the outflow stream. And the velocity in and the velocity out is the same. It's just that we have different mass flow rates because the jet diameter is smaller on the outflow, since some of the flow is redirected by this plate. Okay, so to calculate the effect of all that, we calculate the inflow jet diameter and the outflow jet diameter, the mass flow rate of the inflow, The mass flow rate of the outflow, 86.6 kilograms per second. So far that's making sense. Now, the momentum equation says it's the mass flow rate out times the velocity out. So 86.6 kilograms per second is the outflow mass flow rate. The velocity is out to the right, so we put positive 90 meters per second. And then subtracting the inflow term. So the inflow term is that larger 706.9 kilograms per second mass flow rate and the same 90 meter per second velocity to the right, so the velocity is positive. But what's causing the force that is required to hold the system steady is just the difference in mass flow rates out versus in. So if we do all those numbers, then the force required to hold the system steady is negative 55.8 kilonewtons. So that means you have to press to the left to hold the system steady. So in other words, the external reaction that would resist this fluid jet is pressing on the plate to the left. So of course that makes sense because you've got this big stream coming in and it's going to be changing direction. Much of it is going vertically that previously was going horizontally. So we have to apply a force to the left in order to hold that system steady. But this is asking what force does the jet apply to the plate? So the jet is pushing on the plate to the right. And that's why we have to press externally to the left on the plate to resist that. So be careful about what the problem is actually asking. So that is the force required to hold the system steady, but the force of the jet on the plate is 55.8 kilonewtons, meaning that the force applied is to the right. All right. So any questions on that example? Okay, let's look at this one last example. And this is the trickiest of them all because we've got flow in and out, and the outflow has an X component and a Y component in both the positive and the negative directions. So this is the first time where we're seeing the necessity of that summation term. You know, this is saying the sum of the mass flow rate out times the velocity out in X. So there can be more than one term where there's an outflow. Here we've just got a single inflow term, and that's fine. But there are two outflow terms. And so we know the angle of those jets relative to the horizontal, so 70 degrees here relative to the horizontal. And further complicating things is this time each of the fluid jets have a different velocity. Maybe it looks like V2 and V3 are lower than V1 was. Here in this example, we're assuming that the contact with the plate is reducing the velocity of the jets. Okay, so what we need to do here is calculate the forces of the water jet on the deflection plate. So we'll begin by calculating the force required to hold the system steady, and then this question is asking us to find the opposite of that, because we're asking for the force of the jet on the plate. So as before, we're going to apply the momentum equation both in the X direction and the Y direction separately, but regardless of whether we're working vertically or horizontally, the mass flow rates are what we have to start and calculate. So we have to know what is the mass flow rate of stream 1, what is the mass flow rate of stream 2, and we're using the continuity relationship because look, we know m dot 1 already, 6.7 kilograms per second. So that's the in. And then here at 3, we know the velocity and the diameter of the jet. So you can calculate m dot 3 based on the known velocity, and this diameter will give you an area. But we don't know at location 2 the diameter of that jet. And we don't need it because in equals out. And so the total in is 6.7 kilograms per second, and the total out will be whatever mass flow rate we have at 3 plus the mass flow rate at 2. So in other words, what I'm saying is this problem we're combining the continuity principle along with momentum. So you have to calculate m dot 2 based on what is m dot 1 and what is m dot 3. I'll write a few things on the board, a suggestion of a few things you need to calculate in order to substitute it into the momentum equation. Here it is. All right. So the water comes in at 11.5 meters per second and 6.7 kilograms per second. And then it's deflecting by this plate. Some of it goes down, some of it goes up. So what we know about what goes down is the diameter and the velocity. And then what we know about what goes up is just the velocity. So we can calculate with the diameter that's given, the cross-sectional area, and from that cross-sectional area get the mass flow rate at 3.11 kilograms per second. And then the outflow stream at 2 is just the overall inflow minus the partial outflow at 3. So the mass flow rate at 2 is 3.59 kilograms per second. And then in the x direction, when we calculate the force required to hold the system steady, we've got the outflow term at 2 and the outflow at 3. And so if we look at the sketch here, at 2 the velocity is to the right in the x direction, but it's to the left in stream 3. So we're going to have to be sure that we put a negative sign for the velocity at 3 when we're substituting that in. The mass flow rate doesn't have, looks like I've got a calculation error. I just noticed here I've got 3.11 kilograms per second written there. Hopefully my calculations don't reflect that, because when I was circulating around, does everybody else also have 74.32? So I think I must have just written this wrong, 3.11. Oh, no, that is the right. Sorry. Yeah, that's the mass flow rate 3. All right, I confused myself for a second there. It's two different mass flow rates. There's 2 and there's 3. All right. It would be unusual if I had errors in these notes after so long. Most of the students have already found them. But this minus sign is easy to overlook. Okay, and then we have to apply the cosine of 70 because that's the component of the velocity that will be horizontal. And then here's the mass flow rate in, and no angle adjustment required because the velocity is just in x. Okay, so if the force required to hold the system steady is negative 74.32, meaning that we're going to have to press on this to the left to hold it steady in reaction to the jet, then the jet is pressing on this plate to the right. So it's going to be the positive 74.32 newtons to the right. Okay, now if we just briefly examine what's happening in y, the inflow stream doesn't have any y component. So the inflow term is 0, but the outflow term, there is an outflow that is up and an outflow that is down. Okay, so let's go through this. It's going to be the mass flow rate at 2 times the velocity at 2, and then the sine of the angle to give us the vertical component of that velocity stream. And then in the y direction, but stream 3 is where we'll take into account that negative velocity, 9.9 meters per second, because it was to the left when we were doing horizontal, and it's downward when we're doing vertical. So again, the 9.9 is negative for a different reason, but because it's opposite in the direction that we define as positive. So if the force on the force required to hold the system steady is 7.5 newtons to the right, then what that means is, up, that would be up, then the force of the jet on the plate is net downward. So that's a little bit less easy to just immediately see, whether it's going to be up or down, because, we kind of just instinctively knew that you'd have to press to the left to hold the plate steady. But whether it's going to be vertical up or vertical down has more to do with the mass flow rates and the relative velocities of each of the exiting streams. So 7.5 newtons downward is the force of the jet on the plate. So the plate is tending to move downward unless it's steadied. Any questions on this example? Okay. I'll go back to this in case anybody needs to copy down more of the numbers, but before I do that, we'll just close by taking one last look at these announcements. First of all, the next homework assignment due on Monday, and then the exam on Tuesday. So chapter 4, that is back when we started talking about flow visualization. So like streamlines, streak lines, talking about the flow classification of turbulent versus laminar, talking about flow classification of steady versus unsteady, uniform and non-uniform. We talked about the different types of fluid acceleration in chapter 4, like local acceleration, convective acceleration, centripetal acceleration, Euler's equation, Bernoulli's equation, and the equation for irrotational flow. So there's a lot of stuff in chapter 4, but as complicated as it is, chapters 5 and 6 really only have one idea each. So, all right, that's all for today. I will see you on Thursday.